Okay, so all around us, in pretty much every forest on the planet, there are these secret conversations going on. And they're not spoken, they're not heard, they're written in a language of pure chemistry. Today, we're going to decode one of the most high stakes chemical conversations out there, the one used by bark beetles. I mean, just think about that for a second. It seems completely impossible, right? A single beetle is basically nothing against a giant tree, especially one that has its own powerful chemical weapons. But these tiny little insects, they have a superpower, and it allows them to conquer giants. And that secret, it's all about teamwork. It's coordinated by these chemical signals called pheromones. So a pioneer beetle finds a good tree and basically sends out a chemical shout. Hey, dinner is served, get over here. The problem is, that's not a private phone call. It's more like a giant, noisy party, and absolutely everyone is listening in, friends, enemies, and freeloaders, which makes this a really, really dangerous conversation to be having. All right, so here's what we're going to dig into. We're going to start with the beetles' central problem. Then, we'll look at the huge gamble they take when they call for backup, and we'll ask if some beetles can just cheat the system. After that, we'll see how trees actually fight back, jamming these signals, which leads to this incredible chemical arms race. And finally, we'll try to make sense of all the mixed messages in the forest. So, first up, you really got to get your head around the beetles' dilemma. Their entire life is this series of unbelievably difficult trade-offs. It's kind of like trying to whisper a really important secret in a super crowded, noisy room where you know everyone is trying to eavesdrop. Just think about everything a single chemical signal has to do. It has to attract a mate, right? That's job number one. But it also has to call in just enough backup to overwhelm a tree's defenses, but not so much backup that your own kids starve because there's too much competition. Oh, and you have to do all of this without basically ringing a dinner bell for all the predators and parasites that are out there listening, just waiting for you to make a mistake. It's a nearly impossible balancing act. And that brings us to their core strategy, aggregation. Swarming the tree. But for each beetle, this is a massive gamble. Is calling everyone to the party actually a winning move? And here's the absolute key to the whole thing. What's in it for the individual beetle? Do the benefits of having help to fight the tree outweigh the costs of having to share your food with all those helpers? Well, it turns out the answer completely depends on the tree itself. So let's break this down. On a dead tree, there are no defenses to worry about. So every new beetle that shows up is just more competition, plain and simple. You can see it in that top graph. Success just plummets. But on a live tree, well, that's a whole different ballgame. The beetles absolutely have to work together at first just to survive the tree's counterattack. And that's what you see on the bottom. Success actually goes up as more beetles arrive, at least until competition finally kicks in. And what's so cool is that when you look at the data from the real world, it matches the theory perfectly. See the squares? That's beetles on dead trees. More beetles, less success. It's a straight shot down. Now look at the circles. Those are the beetles on live trees. At first, their success goes up as more of them show up. There's this perfect little sweet spot, an optimal number of attackers where cooperation is winning right before the downside of competition starts to take over. This is amazing because it lets us create a real objective definition for how aggressive a beetle species is. It's just the best number of attackers they need to succeed. So for a species like Ips typographus, which takes down healthy live trees for a living, it needs an incredible 243 attackers per square meter to hit that sweet spot. Now compare that to Ips panaye, which usually just goes for dead trees. Its optimal number is basically 1. Any more than that is just extra competition it doesn't need. So you look at this whole system and you have to wonder, isn't it just begging to be exploited? I mean, if attacking a live tree is so risky and needs this massive group effort, why wouldn't some beetles just evolve to be, well, cheaters, freeloaders? Why not just hang back and let everyone else do the dangerous work first? Well, it turns out evolution is one step ahead. A pure freeloader strategy just doesn't really work out in the long run, and for some really key reasons. First, that pheromone signal, that dinner bell, it's directly linked to the tree fighting back. Once the tree is defeated, the signal fades. Second, if you show up late to the party, you get the scraps, the lower quality food. Third, these beetles don't live very long, so waiting is a huge risk. And maybe most importantly, waiting around just makes you a sitting duck for predators who are also showing up fashionably late to the party. Okay, so let's flick the script and look at the other side of this battle. Because the tree is not some passive victim here, not at all. It is an active fighter, and it has a very, very clever trick up its sleeve. So researchers started noticing something really odd. Sometimes a pioneer beetle would drill into what looked like a perfectly good tree and then Nothing. Crickets. The call for backup just never seemed to go out. And it turns out the tree was actively jamming the beetle's signal. So here's how it works. A single beetle starts to bore in. A healthy tree's response is to unleash a flood of this toxic, super sticky resin right at the entry point. Now, this stuff does more than just try to kill the beetle. It physically traps the pheromone molecules inside the tunnel. The signal gets made, but it can never get out into the air. The call for help is totally silenced. The attack fails, and the tree wins. It's an absolutely brilliant defense. And that brings us to the final, craziest layer of this chemical war. Because it's not just a two-way fight between beetles and trees. Oh no, there is a third party listening in on every single message: the predators. And their goals could not be more different. The beetle needs to broadcast its signal far and wide to assemble its army. The predator has evolved to hear that exact same signal as a dinner bell, leading it straight to an all-you-can-eat beetle buffet. I mean, this is the very definition of an evolutionary arms race. So how in the world does a beetle survive this? It finds a compromise, and this is fascinating. The beetle, Ips pini, has two main predators, and it just so happens that each one prefers a slightly different flavor or version of its pheromone. So what does the beetle do? It evolves to produce a chemical blend that is right smack in the middle. It's not the absolute favorite of either predator. By not being perfect for anyone, it minimizes its overall risk of getting eaten. It's this incredible chemical balancing act. But it gets even cleverer than that. Some of these beetle populations add a secret ingredient to their mix, a chemical called lanierone. Lanierone works like a signal booster. It makes the pheromone way stronger for other beetles of its own species. But here is the genius part. Their main predators either can't detect it or they just don't care. They've essentially created a semi-private channel, cranking up the volume of their own message without making the dinner bell any louder for their enemies. So let's just zoom all the way out. What does this all tell us? We started with a pretty simple question, and we've ended up in this multi-layered world of cooperation, cheating, warfare, and espionage. The single biggest takeaway here is that a pheromone isn't just one clear, come here signal. It's not that simple. It's a whole suite of mixed messages. Its meaning, its power, its effectiveness, it's all constantly being shaped and reshaped by the tree, by competitors, and by the constant threat of predators. And this quote from Kenneth Raffa, the author of the research we've been looking at, he just nails it. He says that what we might typically see as just noise or random static in the signal, that's not noise at all. That variation is the story. It's the physical evidence of this incredibly complex evolutionary dance that's happening all the time. It just makes you wonder, doesn't it? If a conversation this complicated and this dramatic is happening in the bark of a single tree, what other invisible languages are being spoken all around us, shaping our world in ways we're only just beginning to figure out?